What is LVDS? Low voltage differential signaling anyway. Got lots of feedback from my last video on reusing old laptop displays, and some of you have been asking, what is LVDS? How does it work? What does it do for me, etc. And it's not actually that complicated, so let's dive into it. Hi there, welcome to the breadboard. I'm Peter and this is my channel, and we're going to talk about LVDS. I have not delved into a techie subject like this for a little while, and this is the first time I'm using this particular recording setup, so hopefully it'll all go well. LVDS, low voltage differential signaling. It's been associated with screens for a long time, but it actually has nothing to do with LCD panels or something like that. It's just that that technology has started to use LVDS to such an extent that it has become synonymous with that. And so when people talk about LVDS, they are often talking about LCD serial interfaces to get the RGB signal up into the display for displaying for you. So let's go back to some basics and have a look at exactly what it is. Okay, so LVDS in its simplest form, well, I say simple, it's going to get a little bit techie in this conversation, is a differential signaling that can work at very high data rates, and you'll see why that is relevant in a little while. So here's just a little extract from a manual I got from Texas Instruments website. I'll put all the links in the description so you can have a look at these yourself. And this is just looking at the speeds that you can get. And LVDS, which is the one we use, maximum data rate can go as high as 3.1 gigabits per second. So that's pretty high speed. Other ones go a little slower, like different technologies here. 8 meg, 250 megabits, 800 megabits. The little b means bits, not bytes. If it was bytes, it would be a big B. One of the things to note here about LVDS is the fact that the output swing is only 350 millivolts. It's the lowest voltage swing out of all of these different standards. Anyway, things like RS-232, RS-485, and other serial buses like that are up in the many volts, and therefore they get, they're dissipating power-wise maybe 80 to 100 millivolts to do their job. LVDS is way lower than that. It only dissipates, a couple of milliwatts, I think, because it's using such a low output swing. Now, the other part of LVDS is that it as a differential signal, let's forget the LV part of it just for a moment, is that with a signal wire, if I find the right, here we go, here's a good picture. Normally what you would have is one leg, let's just say a simple switch, one leg or for a bulb or something like that. One leg might be ground and the other leg would be the signal. So you've got an output voltage going out and the ground provides a return path. The problem with this is that you need to be able to detect and ignore noise. And a ground could have interference on it, so relative to the signal, it could be varying and giving you false data. A differential signal doesn't necessarily rely on a ground for the actual data. It uses two lines and they switch polarity, so you could have one high, one low, and then when it goes from a 1 to 0, they would switch completely. So you're measuring the difference between them. And then they have this thing called common mode rejection, where those two signals can float around relative to ground and still be perfectly valid from a signal perspective. And what we have here is an example of that. This is a common mode voltage. So you've got a swing of 400 millivolts here, and it can be between 1 and 1.4 volts to 2.4, 0 and 0.4. The point is, you can see here they're switching, and it's the difference between these two lines that gets the data to go across very reliably. Even if there's some noise, that is making these two wires go up and down in voltage relative to ground. I'm not going to go into it much more than that. You can read this data for yourself, and I want to try and keep this thing fairly simple. So the differential part is about noise immunity and getting some distance. Because you're not relying on the ground, you can go over quite a distance in this case. The low voltage is a way of reducing the power dissipation of the signaling. So that's the LVDS. Now, what do they do for video, which is why you're obviously watching this? With a typical screen, LCD screen, so it could be any panel you like, really, even old monitors. You've got three colors that make up the screen. You've got red, you've got green, you've got blue. And you've got pixels. So a typical screen, 1920 by 1080 pixels, so 1920 by 1080. That's typically called a 1080p monitor. At every intersection of that XY resolution, there is a pixel. And a lot of modern screens will have 24 bits per pixel, or in a slightly cheaper monitor, you may only have 18 bits per pixel. Now, that represents, for the 18, which is called a 6-bit monitor, when you look at the LVDS or the screens, they'll be described as a 6-bit screen. You'll have 6 bits for red, 6 bits for blue, 6 bits for green. You also need a horizontal and vertical sync, which tells the screen when to go back to the beginning of the line, or when to go from the bottom of the screen back to the top and start rescanning again. I'm trying not to go into all the details of how the raster screens work and all that kind of stuff, but suffice to say that the horizontal sync makes it flip back to the top, and the line sync makes it flip back from the right hand side of the screen back to the left hand side. All of this data, so there's 18 plus your two syncs, that's 19, that's 20 lines, has got to get up to the screen. That's a lot of wires you've got to get up there. When you go to 24-bit screens, obviously that's even more lines. You've got 24 data lines, and then you've got your horizontal vertical sync. You're going to have a clock as well. You have the clock on both of them, by the way. And your TTL screens, especially when you get to some of the really small ones that you can get for Arduinos and things like that, they will have red, green, and blue, all as individual lines, but the data rates are not very high, so you can do it. When you want to start trying to get that kind of signal up to an LCD display that's pretty high resolution, that's a lot of data you're trying to pump up, and it gets very expensive to run those wires up there. So they came up with a way to reduce the number of wires going to the screen and also maintain this high data rate, and that's where they use the LVDS specification, which is actually the physical specification, not the protocol, to get that data going up. Now, what are we doing here? So what you've got is, if you get the right one here, we've got what I'm showing you here is a basically parallel to serial or to LVDS converter. This one is from Texas Instruments. It's a 75 LVDS83, and what it does is it's got 4 bytes of data, so that's 24. 3 of those would be used for, in our case, color, or 24 bits of color plus something else. Now, as you said, LVDS is actually got nothing to do with video specifically. It's just used in video interfaces to these LCD panels. So this could be used for anything. So this chip gives us 4 bytes or 32 bits of data, and it serializes it down to 4 LVDS channels. Now, the 5th channel that's going out is a clock, so that it can synchronize things. There's a weird thing with the clock we'll have a look at in a minute. So the input to it is the 32 bits of data and your clock. We'll ignore these other interfaces for now. At the other end of the line, i.e. in the screen, we've got a receiver which takes the 4 lines of data and our clock, and it brings it back out to our 32 lines and a clock here. Now, I keep saying screens because that's what we're talking about, but this can be used for anything. If you were driving a bunch of LEDs for a display, or you were maybe you had 32 channels of RS-232 or something like that you wanted to send over a distance, but you didn't want to have 32 or 64 wires. You wanted to be able to minimize that. Well, this is a way of doing it. You can just have your 32 lines coming out. The other chip will have 32 in. You only got 2, 4, 6, 8, 10 wires going across. Now this could be RJ45 connector twisted pair wire. The whole thing about this is it's designed to go over low-cost twisted pair cabling. And if you look on my starting screen, let me just bring that back a second. Right here, you can see we've got you can see these blue and white wires. Those are all the twisted pairs and everything that are being sent up to that. And that was a LVDS video LCD screen connector. That's what that's what it's doing for us. It's sending the serial. It's basically a parallel to serial, back to parallel kind of thing. And it's designed to be immune to noise, take up less low power, etc., etc. Now, how does that rate for us? Here we have a data sheet for one of the LCD panels I have. It's actually a 10-inch one, but it's a 1366 by 768 display. A lot of the panels I have are that resolution. And you can see on the left here, remember we just looked at those chips and we talked about the fact that we've got the 32 bits of data and we've got the clock. So here we've got 8 bits plus 8 more, plus 8 more, plus 8 more. This is what is referred to as a single lane or single port LVDS interface. And most of the screens I was using in my previous video were single lane LVDS. Now I'm going to be showing you more videos in the future where I'm going to actually be using bigger displays, and because they're bigger they actually require 2 lanes. I'll explain in this video why that is, but for now we'll just look at the one because the principles for both of them are exactly the same. How has the LCD monitor folks decided to use this LVDS chip? Now, they've taken these 8 data lines. Now, what we're seeing here, by the way, is this gray area at the beginning. That is the previous. This one in the middle that's white is the current pixel being transmitted. This one on the extreme right that's gray again is the previous pixel that was transmitted. So the data is basically streaming from left to right down the LVDS cables and coming into the LCD monitor, being decoded back into the full 24 bits or 18 bits, depending on whether it's a 6-bit or 8-bit monitor, and then driving the screen. What we can see here is that this first line, RA, RB, RC, RD, these are the 4 separate LVDS twisted pair wires going up to the screen. You've got G, which actually means green, and then you've got red 5, 4, 3, 2, 1, red 0. So there are 6 bits of red data right there. There's 1 bit of green data. Then you've got the other 5 bits of green data here and 2 bits of blue data. Then you've got the rest of the blue data. Then you've got horizontal and vertical sync, and then you've got a DE. What DE for? Not sure. Anyway, so the screens that I was looking at in my previous video, they were 6-bit screens. So they actually only had 4 twisted pair wires. One was for the clock, and then there was RA, RB, and RC. It actually didn't need RD, which brings in the extra 2 bits of data for when you have a screen that supports 16 million colors as opposed to 262,000 colors. And you can see here, this last one, the last bit is not used, and then we've got a red bit 6 and 7, green bit 6 and 7, and a blue bit 6 and 7. So that's the final bit of the color map. All of these get sent together across those 4 differential lines and are clocked in and then appear at the exact same time after that decoding chip so that it can be pushed up to the screen, and that represents 1 pixel. So this is kind of an indication as to why the cable is critical in LVDS, getting the right one for the right screen, because if you have an 8-bit screen, which is the full 60 million colors, 8 bits per color, then you need to have the 4 channels for the color information, as well as obviously horizontal, vertical sync, and then the clock. So you'd see 5 twisted pair wires as opposed to 4 twisted pair wires. You've got power and other signals going up there as well, of course. The reason that the horizontal and vertical sync is in RC is because you don't always need RD if you're running a 6-bit screen. And if you have a cable that supports an 8-bit screen and you're using a 6-bit screen, as long as the transmitter and has been set up correctly, this last cable just wouldn't be used. So if you're buying a cable specifically, you could always err on the side of caution and get a 8-bit cable instead of a 6-bit cable. It probably won't cost you any difference in price. So that's the way that works. That sends up this data at really, really fast data rates. Now, because some of these screens want to work at 120 hertz, 1920 by 1080. If I just bring up a calculator a second. So 1920 by 1080, right? That is 2 million pixels. Now, let's assume it's a 16 million color display. So multiply that by 24 bits of data. Right, now we're ignoring a little bit because we're not including the horizontal vertical sync or the clock yet. That's 49 million bits of data. That's just one frame, and you're doing let's just say 120 frames a second. So multiply that by 120. That's 5,971,968,000 bits per second that has to get sent up to that screen. That's an awful lot. And if you're trying to send that up without some kind of control, you're not going to be able to do it very well. This LVDS interface can run, as you saw at the beginning there, at some phenomenal data rates. So you take your parallel data, your RGB data, you stick it into this chip and it squirts it down the line. Now, we can't get that all down one wire because that's 5 gigabits. So we have to divide it down. And depending on the quality of the chips and the cables, it could be way less than you think what the theoretical maximum is that you can achieve. So we've got 7 bits per cable, and we've got 1, 2, 3, 4 cables. So if we divide this by 4, now we've got 1.5 gigabit going down that cable at the 120 hertz. That's a huge amount of data in anybody's book, but that's what the LVDS interface is doing for you. It's squirting down that data into that screen, and it's putting this many bits down basically in every second to drive your screen. If you have a higher than 1920 by 1080 screen, you're probably not even going to get all your data up those wires in time with just one lane of LVDS. So what they do is they introduce the second lane, which gives you another 4 channels for color. So this would be the odd lane in this case, and the other one would be called the even lane. It would be laid out pretty much the same, except the clock, I think, is skewed slightly, and it sends the data all in parallel. So now you get 2 lines of data at a time going down the screen, which is why the LVDS is doing that. And that's why you have that other cable, which has even more wires in it. The one thing I want to point out here, which you may have already noticed, is this is the clock. Our clock plus is the clock going up the cable. But you can see here, there's only 1 clock cycle for 1 frame of data. There's 7 bits of data here, but there's only 1 clock cycle. Now, if we go back to the receiver, this one, here we go. You can see at the bottom here, let me just scroll it up a little bit, make it a bit bigger. This is the clock in. It's actually it's a phase lock loop, and it's actually multiplying the clock by 7. So a little bit of magic going on inside the silicon there, which allows you to recover your clock from a lower speed clock. So this clock is only running at 1/7 of the data rate for a line, and so it can clock it in and it would synchronize with the phase lock loop, etc. Yeah, so that's what that's doing for us. Let me just zoom out a little bit again. So if we go back to the actual LVDS cables, what is this one for? This is for a big screen. There's that one. Okay, going back to this, this is for my 10-inch 1368 by 768 screen. So this last bit, it's actually not a, it's only a 6-bit LCD panel, so it doesn't use this last channel here. Here we go. You can see it's a 40-pin connector, and if you look at what's on here, you've got pin 1 is test, it's not used, so 2, 3, 4. First few pins are the power for the LCD panel and the EID chip. Now, most of the controllers that we've looked at in the previous video, and we're going to look at, don't actually read the EID. You configure the board for the screen that you're using it with, and most of them can be reprogrammed if you've got the right programmer. So we've got 3.3 volts. Important to know what your panel uses. And most of the small ones I've seen, in fact, every one of the smaller screens, 15-inch or so, 1368 by 768, sorry, 1366 by 768, are all using 3.3 volt panels. Then we have our ignoring the EID because, as I said, it's not using it. Our controllers aren't. Actually, let me just say, the EID is actually just an I2C interface. It just reads an EEPROM with data in it. So here is our LVDS signals now. In this case, it's RX in 0. Now this is received because it's actually from an LCD panel's perspective. So it's input 0 plus and minus because it's differential, input 1 plus and minus, input 2 plus and minus, and then the clock. So that's one channel, 2, 3. So there's not 4 channels. As I said, it was ignoring the 4th one because it doesn't need it. And then we've got the clock. And then we've got a bunch of not connected pins. The grounds are connected. This one here, 2021, is where if you were using an 8-bit screen, you would have the RN3. And if I go back to this screen here, you can see here it's got the RN0, RN1, RN2, and then there's an RN3. RO3. There's the clock, and then there's the RO3 after the clock. There, RO3 plus, RO3 minus. So I'm not going to dwell there for a second. Then you've got a bunch of not connected, and then you've got power for the LED, ground and positive. And you've got the PWM signal for changing the brightness and a control to turn the LED panel on and off. These pins, the 31 through 40, you notice they're all dedicated to the LED display. What you'll find is when you get panels that have the CC the cold cathode lights on them for illuminating the panels, it's not carried on this connector. You'll find most of these bigger panels with CC cold cathode displays, sorry, cold cathode backlights, the power for that is being carried over separate wires. Probably because there's a bit more noise associated with those because they have these high frequency oscillators generating close to 1,000 volts at the other end at the cold cathodes. So the 40-pin ones tend to be the LED displays, or that's what I found so far. And these, you know, from pin 30 to 40 are all to do with the LED display. And you can see this is just a single lane 6-bit because there is no twisted pair wire for the 8th bit, which would be roughly here. Okay, so now let's look at a bigger screen and see what differences we get with a bigger screen. So the one I'm looking at actually has a display of 1680 by 1050, so it's considerably bigger. And it is also, I think, a full 16 million color. It's got a number of different inputs. Let's see if I can see how many colors it actually, does it say? Yeah, full 16.7 million colors. Okay, so here is the LVDS interface for this screen. And you can see here that it's only a 30-pin connector. This is because it uses a CCFL backlight, and that is being powered via completely independent cables, probably because they're connected to a high voltage generator, which generates somewhere around the region of sort of 700 to 1,000 volts for driving those CCFL bulbs. A little bit like a fluorescent tube. Actually, they're a lot like fluorescent tubes. Anyway, LVDS interface for one of these. Full 16 million colors, which means you need 8 bits for red, for green, for blue, so 24 bits of color data, plus a horizontal and vertical sync. So as we saw way back, where was it? Yeah. Basic principle of the data rate is the same, but now we're actually leveraging this RD line, which has the extra 2 bits for each color. So we've got our odd signaling lines, 0, 1, 2, clock, and then now, because it's 8-bit, we've got the additional data line, twisted pair differential, for that 8th or 4th signaling line. So this one here, RD, that's this RO3, RX03. And then we've got, because it's such a high resolution at 1050, we now have the Evenside drivers, so that we're actually driving data for 2 pixels at a time. So here's our RE 0, 1, 2, clock, and 3. So again, 8 bits per pixel. And then we've got power for the panel, and a lot of these panels are actually 5 volts when they start getting bigger. I haven't seen any 3.3 volt ones yet. All the smaller ones were. So 5-volt panel. So this, when you're configuring one of these controller boards to use these, you need to make sure that you look at what the panel voltage is, as well as whether it's 6-bit or 8-bit. Right now we're talking about LVDS and what is it, so I'm not going to get into it in this video, but when my other controller cards come, I will talk about that in those videos. So, yeah, 30-bit connector. This physical connector is actually bigger than the 40-way connector as well, probably because it's carrying more power for the panel on the 5 volts, and I'm not sure what the other reasons why, but it's basically the same principle, and the pinout is almost identical, but you do need to just make sure that you're getting things correct. For instance, the pin 27 on this panel is ground, and pin 27 on this panel, let's find it, is not. It's a plus 5 volts. This panel, by the way, is a 1080p panel, so that's a full 1920 by 1080. So you've got to be aware of that. In the case of the cable, I bet you probably find, when we look at it in the next video, that that connection is actually not connected. Either that or the data sheet is incorrect. So that means now we've got 2 sets of LVDS lines, and we've got 8 bits per pixel, so we're keeping our clock data rates low relative to the overall bit rate that we're sending to the panel. So that's, if we then go to a bigger panel, which is so that previous one here, this is a 20-pin, this is a 20-inch panel. This Acer H243H is a 24-inch panel. But you can see, basically, it's the exact same connection. I'm not going to go into all the details of the panel, but suffice to say that you're using a cable which has 2 lanes of LVDS, and each lane because it's going to be 8-bit, will have 5 twisted pair cables. So if you're looking at a cable, then you would need to make sure that you're getting one with all of those connections on it. So if I just bring up an image for a second, if I can find one, I'll zoom that out. You can see here, this one actually has, so that this is the starting end. So this has got 1, 2, 3, 4, 5, 6. It looks like he's got 6. They've got 1 pair there, 2 pairs, 3, 4, 5, 6. Yeah, it's got 6 pairs on this one. So this is probably just you've got 4 for the data and 1 for the clock. So this might actually have one that reads the EID on this particular cable as well. That's that I2C cable we looked at a little bit earlier. But you can see this one is certainly not a 2-lane LVDS. It's only a single lane. There's just not enough twisted pairs in there. If I try and find a 2-lane version. All right, I got a few I'm just Googling right now to look at this. So here's a connector right here, and you can see this is a 30-way connector. It's a bit bigger than the other ones. But you can clearly see that it's only a 6-bit panel, and it's only a single lane. So you can see here, this one, if I can get it to say still, no, I can't get it to say still. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 twisted pair cables clearly visible on there. They actually don't have power lines going to the panel on this particular one. You can see there's 10 twisted pair cables. So this would be a 2-lane 8-bit cable. So at the end of the day, there are a few combinations of LVDS connectors when it relates to LCD panels. You've got single lane, 6-bit or 8-bit. You've got dual lane or 2-lane, 6-bit or 8-bit. And that makes a difference as to whether it's 4 twisted pairs for 6-bit or 5 twisted pairs for 8-bit. And 5, let's assume 8-bit for now, 5 twisted pairs for a single lane, and you would see 10 twisted pairs at least for a dual lane. Now when you get to bigger monitors like 2K screens and 4K screens, I wouldn't be surprised if there's an even bigger connector. I haven't seen any of them yet, but I would assume you're probably going to be looking at least a 50-way, so maybe 3 LVDS lanes or even 4 to drive these really big screens. It's all about data rates and getting the quality. So this picture I just put up here, the one I showed you at the very beginning of the video, this is actually a oscilloscope capture of an LVDS signal. It's only a single channel, so 1 differential pair. But what you can see is, here the signal where one line is going from low to high, the other one is coming from high to low as it goes through there. And this is actually called an eye diagram. Won't get into too much details, but I think it looks kind of cool. Anyway, what this ultimately amounts to is that there will be a number of different connector styles depending on how many lanes, whether it's 6-bit or 8-bit, and whether it has 1, 2, or 4 LVDS channels in there as well, or lanes. And one place I go to find out exactly what I'm dealing with, which will help you identify the cable, is a website called panellook.com. Let me just bring that up. So here it is. And what I have is 2 of my bigger panels. Let me just also bring up one of my smaller panels as well. I have a little Word document here with a bunch of links to it for some of the panels that I have. Just bring up this one. So this is my 10-inch panel, which I showed you one of the connectors of, and you can see here the information it gives you. It's an LG display, 10.1 inch. Tells you the resolution, 1366 by 768. So that'll help you pick a controller right there. You know the resolution you're going for. The screen size really doesn't matter too much. The next thing of interest is further down here. You can see it's only got 262K colors supported. And further down, we can see it's a 40-pin interface. So it's a 40-pin connector. That pretty much tells us that it's probably going to be an LED backlight. And it's an LVDS 1-channel 6-bit. The other important piece of data is it's a 3.3 volt display. So you don't want to be feeding it 12 volts or 5 volts. You want to give it 3.3 volts. Now, a couple of my other screens. Here's my one that I've actually going to be taking apart and connecting to a controller as well, just because I can. This is a 20-inch Asus, I think, or Acer Screen. Its resolution is 1680 by 1050, so it's a little bit bigger. And what you'll notice here is it's full 8-bit color, so 16.7 million colors. 30-pin connector, that's because it uses a CCFL, cold cathode fluorescent tube, for the backlight. And it's an LVDS 2-channel 8-bit connector. And it's 5 volts. So any controller board you get, you need to know that you can... they typically will have a jumper on, so you can jumper it for 5 volts or 3.3 volts, and sometimes it even has a jumper to let you go as high as 12 volts. In this case, you'd want a 5-volt supply for the panel, and it needs to be a 2-channel 8-bit connector as well. So that 30-pin connector is going to have 10 twisted pair wires on it at least to cover the amount of wires you need to get this data rate, right? Because you've got 8 bits, which means you've got 4 LVDS data lines just for the RGB data, and then you've got the clock, which makes 5 pairs, and we've got 2 channels, gives us the 10 pairs. CCFL, so that's going to be powered separately, not via the connector. I've never seen a CCFL one yet that gets powered by the connector. Now my other screen that I've got, which I haven't pulled apart, but I did pull up the service manual for it, is an Asus 24-inch screen. This is a full 1920 by 1080. And so the important data, if you're looking for a controller here, for the LVDS cable, is down here. So we got full 16.7 million colors. That immediately tells us it has to be 8-bit. And it's LVDS. In this case, it's 4-channel 8-bit. So you're going to have 5 pairs per channel. So that's 20 channels. That gives you 40 pins right away just for the data with the clocks. So in this case, it has a 66-pin channel, 66-pin connector. I was slightly underestimating the number of pins. And it's a 5-volt panel. And in this case, it's also a LED panel. So it could be that because it's 66 pins, it's probably using some of those pins for the LED. In fact, I think I've got the data sheet for it up here. Yeah, right here. So this is it's an AUO screen. Let's just see if we can find the LVDS connector and see. Okay, a little bit of conflict here. M240HW01. So I've just proved to myself an important feature that you have to watch out for is the version number of the display, the panel that you have. If we look in this one, this is a V0 panel, which is the one I actually have, as borne out by the manual that I opened over here. Where is it? Let's just get rid of that. Here. Right, this is the manual for my screen, and it shows me the panel is the V0. The one I opened before was the V8, which is obviously going to be a much newer model or better model. So the V0 is actually 60 hertz, and it has a 2-channel 8-bit 30-pin connector, CCFL, so cold cathode fluorescent backlight. The V8, which is this one, has a 66-pin connector, 4-channel 8-bit LVDS interface, and is using an LED backlight. All right, so I'd imagine that this one, I mean, 4 channels at 8 bits, that's 20, 40 connectors just for the data and the clocks. A few connectors for the power. You could probably get away with 50 odd pins if you were, well, you'd probably find that if it was a CCFL panel with this, it would probably be a 50 odd way connector. In this case, because the LED is there as well, it's going to be probably quite a big LED. They're using a 66 pin connector, so yet another one. I don't have any cables that big, so I'm not going to be able to I wouldn't be able to play with this one even if I wanted to. But being that this is the panel that I have, I do have a 6-bit connector, but I think I don't know if it will work. It might work, but just give me funny colors. I'll have to configure that up and try it. But anyway, in your search for a controller, and even more importantly, the cable for the LVDS connector, it is very important that you use a site like panel or panelook.com to get the correct details for your panel, and make sure you consider the version number of the panel. As you saw there, I could have easily wasted some money buying a controller for a panel that I don't have. So I think that pretty much completes everything I wanted to go through. Hope you enjoyed the video. A few of you were asking about more information on LVDS as it pertains to LCD screens, etc. So I hope that gives you enough of a background in it to understand. And when you think about it, it's really just a whole bunch of parallel RGB data serialized down some data lines. And you can't put it all down one data line, because then you'd be having multi-gigabit data, and you'd have to have some very special cables to be able to transmit that without losses. So keeping the data rates to a reasonable level and still hundreds of megabits, you're reducing 50, 100 separate lines for RGB data down to 10, 20 cables, twisted pair, differential pairs, etc., to get it from your controller board up to the screen. I will do an experiment now that I've gone through this, where I'll take a Cat5 networking cable, maybe a Cat6 one, anyway, one that's good for gigabit, and hook it up to an LVDS controller, and maybe have a 10 meter, maybe not a 10 meter, but maybe a 4 or 5 meter length of network cable, and see if it actually works. Because you know what, it might, which will make for some very interesting possibilities. One of these panels, out of its case, is very thin, very low profile. If you can have just a single cable running, maybe a few feet to even a couple, 3 meters away from the panel, that means that you could hide all of those. Okay, just to close off with, there are a number of pretty good resources if you want to get much more into depth with LVDS. Some of which is on the Texas Instruments website. I'll provide some of the links to the ones that I have here. So you got the LVDS Owner's Manual, that's where I got my little picture from, which goes into some details about LVDS, how it works, all sorts of technical information, far more than I need to talk about in the case of using it from a practical perspective for screens. But if you're designing things, then this will make good reading. Texas Instruments also have a number of other publications that you can get. So this one is, let me just shrink it down a bit so you can see. Overview of LVDS technology, application notes, etc., etc. And then, of course, you've got data sheets for some of the chips that I talked about for LVDS. Now, a lot of panels and controllers don't use these specific chips. They've actually integrated them into the silicon in order to keep costs down and things like that, or their own versions of them. But the LVDS, it basically works the same way. These chips here use sets of 8 data lines for each LVDS channel. In the ones that I've been showing you for the screens, they tend to be just pumping down 7 bits of data on each line. So they've optimized it for the amount of data they need to send versus the cabling and various other things. It's all about saving pennies and things like that, right? As I said, and then for your panels, go to panellook.com. I'll provide a link to their base site too. So as long as you got your make and model number of the panel that you're using, you can look up the details there. I haven't found one that's not been there so far, and you can glean all the information you need to be able to decide what controller and especially what cable you need for your panel. If your panel is 1920 by 1080 and it's a little bit older, so it's not 120 hertz, like it's just 60 hertz or less, well, 60 hertz, then one of these controllers that I'm showing in the previous video or in the upcoming videos should work for you. If you're a 120 hertz type high-res panel, then they're not going to work because they're not going to have the 4 LVDS lanes that would be required to drive them. Anyway, that's everything for this video. As I said, popular demand. My previous one was extremely popular, which I was very happy to see. This one is addressing some of the questions that were being asked. My next video on this topic will be more practical about picking boards and how to configure the boards and use them, including reprogramming one of them if necessary to match your board. So that's it. If you liked the video, give me a thumbs up. If you didn't, well then don't. And I will see you on the next one.